So we saw that we can calculate the mass percent from a chemical formula. But what if we don't have the molecular or the chemical formula? We have to use laboratory analysis by using the mass percent to figure out what our chemical formula is. But when we figure out what our chemical formula it is the empirical formula. And the empirical formula is a representation of the simplest whole number ratio of our atoms in the molecule. So we have our empirical formula here as 1 to 2 to 1 ratio of carbon, hydrogen, and oxygen respectively. But the molecular formula is the multiple of the empirical formula. It represents the actual number of elements that are present in the compound. So if we do a laboratory analysis and we end up with this ratio, this is our simplest whole number ratio. It does not necessarily mean that we have formaldehyde. It could mean that we have acetic acid, because acetic acid has a 2 to 4 to 2 ratio, which in simplest whole number terms is 1 to 2 to 1. So all of these are a multiple of 1, 2, 3, 4, 5, 6 of our empirical formula. But they are all different species because they have different formula mass. So let's see how we can calculate the empirical formula, and then we can figure out the molecular formula from there. Okay, so let's do an example in which we have a sample of a compound that decomposes in the laboratory to produce 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Let's calculate the empirical formula. Now, remember, the chemical formula is a ratio of moles of constituent elements, not grams. So we have to, the first step that we want to do is convert our grams of each element into moles. So we have 165 grams of carbon, and we want to figure out the number of moles of that. There's 12.0 grams of carbon for every 1 mole of carbon. And then we have 27.8 grams of hydrogen, and we have 1.01 grams of hydrogen for every 1 mole of hydrogen. And then we have 220.2 grams of oxygen, and we have 16.00 grams of oxygen for every 1 mole. Okay, and then we find that this gives us 13.74 moles of carbon. This gives us 27.52 moles of hydrogen, and this gives us 13.76 moles of oxygen. But remember that we are figuring out the smallest whole number ratio between carbon, hydrogen, and oxygen, and this we can simplify this. So how do we simplify it? We divide by the smallest number of the three, which is 13.74. So now here we get 1 mole of carbon. Here we get 1.99. We can round that to 2 moles of hydrogen. 1.99 is very close to 2, so we can go ahead and round that up. And this, we will get slightly over 1 mole, so we can just say 1 mole of oxygen. So now we figured that the carbon to hydrogen to oxygen ratio is 1 to 2 to 1. So our chemical formula becomes carbon, hydrogen with a subscript of 2, and an oxygen. So this is our empirical formula. Now sometimes in the laboratory we're given, like in this, a laboratory analysis of aspirin determines the following mass percent composition, and it's given to us as a percentage. How to find the empirical formula from there, given the mass percent composition? Well, since all of these here add up to 100%, we're going to say, let's pretend we have a 100-gram sample. And so if we had a 100-gram sample, then it'll have 60 grams of carbon, 4.48 grams of hydrogen, and 35.53 grams of oxygen. So now that we have this in terms of grams, we can convert them to moles like we did in the last example. So here we have 60.0 grams of carbon, and we want to convert it to moles because we need to have a molar ratio for our chemical formula, not a mass ratio. So we have 4.48 grams of hydrogen, and we want to convert that into moles of hydrogen. And we have 35.53 grams of oxygen, and there's 16.00 grams of oxygen for every 1 mole of oxygen. Now we plug this into our calculator, and we end up with 4.995 moles of carbon, 4.436 moles of hydrogen, and 2.221 moles of oxygen. Now, we don't want to keep this ratio because this does not look pretty. We want the simplest whole number ratio of carbon to hydrogen to oxygen. So we divide by our smallest number, which is 2.21. So this gives us 1 mole of oxygen. Here we have 1.997, which is close to 2 moles of hydrogen. And here we have 2.21, about 2.248. Okay, we can't round this up. See, 1.99 or 1.97 is close enough to 2 for us to round. But this is 2.25, so it's a fraction. But remember that empirical formula is the simplest whole number ratio. So let's make this into a whole number. We have 2 1/4, right? So let's write this as an improper fraction. 2 times 4 is 8 plus 1 is 9. So this is like saying 9/4 of mole of carbon. And then here we have the 2. And here we have the 1. Okay, now to get rid of this fraction, the easiest way is to just multiply by 4. Multiply all these numbers by 4. So here this cancels out, and we have 9 moles of carbon left. So here we have 9 moles of carbon. Here this becomes 8 moles of hydrogen. And here this becomes 4 moles of oxygen. Remember, when you multiply one number by 4, you can multiply all of them by 4. So that's within the rules of mathematics. So our empirical formula becomes C9H8O4, and that is the simplest whole number ratio that we have. Okay, so let's talk about molecular formula. And remember, molecular formula is a multiple of our empirical formula, and we multiply it by a factor. I want you to think about this as a square. If I tell you I have a square with dimensions that are 1 to 2, okay, so its width is 1 and its height is 2, but that's its dimensions in the simplest whole number ratio. It's got a 1 to 2 ratio. Doesn't necessarily mean that my square will always be 1 foot by 2 foot. It could be a scale up of that. It could be multiplied by a factor of 2, and my actual square can have 2 by 4 dimensions, right? So I want you to think about the empirical and molecular formula the same way. In the laboratory, we figure out the ratio in the simplest whole number ratio, okay? But our actual molecule could be more than that, but it will still be multiplied by that factor n, which is what we multiply it by here. And n is figured out in terms of empirical and molecular formula by our given molar mass. So you're given the molar mass of the unknown compound, and you determine what the empirical formula molar mass is using the methods that we've just learned. And when you divide those two, you end up with your factor n. And to figure out the molecular formula, you just multiply your empirical formula times n. Okay, let's do an example to understand this. You have that naphthalene is a compound that contains carbon and hydrogen, and naphthalene is found in mothballs. So its empirical formula you figure out to be C5H4, and its molar mass that's given to you for the unknown compound is 128.16 grams per mole. Okay, so what is its molecular formula? Okay, so this is, we know the empirical formula, and it has to be multiplied by a factor n to figure out what our molecular formula is. So how do we figure out what n is? N is our given molar mass divided by the molar mass of the empirical formula. Okay, so our given molar mass is 128.16 grams per mole, and our molar mass of our molecular formula can be figured out from here. So C5H4 has a molecular or a formula mass of 64.09 grams per mole. Okay, so we divide this here by the molecular formula mass that we just figured out for our empirical formula, and this gives us a 2. So our n is 2. So that's the factor that we need to multiply our empirical formula by to get our molecular formula. So C5H4 times 2 gives us C10H8. And this is the molecular formula, what we actually have existing in our molecule. Okay, go ahead and give this a try on your own. Butane is a compound containing carbon and hydrogen, and it is used as a fuel in butane lighters. So what you use to light up your stovetop or a cigarette. Its empirical formula is C2H5, and its molar mass is 58.23 grams per mole. Find its molecular formula. Okay, so we want to find n, and n is our given molar mass divided by the molar mass of our empirical formula. So here, this is 58.23 grams per mole, and then we calculate what our molar mass is for this empirical formula, and it's 29.07 grams per mole. So we divide that here, and this gives us a number of 2. So our N is 2. That means we have to multiply our empirical formula by a factor of 2 to get our actual molecular formula. So it's C4H10. Okay, let's say that you weren't given the empirical formula, and so you have to do both, calculate the empirical formula and then the molecular formula. So a compound with the following mass percent composition has a molar mass of 60.10 grams per mole. Find its molecular formula. Okay, so we'll do this like we always have. We have to convert our grams into moles. And we will, since all of these add up to 100%, we will assume that there's 39.97 grams for every 100 gram sample that we have of the whole compound. So, and then we have 13.41 grams of hydrogen. There's 1.10 grams of hydrogen for every 1 mole. And here we have 46.62 grams of nitrogen. And there's 14.01 grams of nitrogen for every 1 mole. Okay, so we end up with 3.32 moles of carbon, 13.28 moles of hydrogen, and 3.32 moles of nitrogen. But we want to do the simplest whole number ratio, so we divide by the smallest number. And we end up with 1 mole of carbon, or 4 moles of hydrogen, and 1 mole of oxygen. So our empirical formula is CH4O. Its molar mass, its formula mass, is 30.06 grams per mole. Now we're given the molar mass of the actual compound, the molecular compound. So we will use our N, which is our given molar mass of 60.10 grams per mole, divided by our calculated molar mass from our empirical formula, which is 30.06 grams per mole. So our N is 2. Therefore, we have to take C4 or CH4O, multiply that by a factor of 2. And this gives us C2H8O2. And this is our molecular formula.